Okay, so going back to what we learned at the end of class on Monday, we were talking about these counter ions. So these are spectator ions. They don't influence, we're in the weak acid, weak base section. These spectator ions don't influence the acidity or basicity of solution. So these are the anions for strong acids and the cations for strong bases. So these on their own don't influence acidity or basicity, but if one of these ions is combined with a conjugate acid or conjugate base, then the other part of the molecule, not the ion, but the other part of that, we're calling it a salt, does have acid-base properties. So we were looking up here at a weak acid, acetic acid, I think that is, and its conjugate base, acetate, over here. So acetate has basic properties. So if you combine acetate, which has a -1 charge, with a cation, which we did down here, this now has basic properties because the K, potassium, that cation does not have any acid-base properties, but this is the conjugate base of an acid, so it is basic. So on the next slide, we looked at the first example here. We said NH4Br is acidic. So NH4Br, we have Br minus, which is one of those counter ions with no acid-base properties. Then we have NH4 plus, which is acidic. It's a conjugate acid of NH3. So if you add NH4Br, ammonium bromide, to solution, you're making that solution basic. Or sorry, acidic, because you're adding an acid, the NH4 plus. So looking at the second molecule, to do this, we first identified what the cation and anion were. So the cation here is sodium. We have 3 of them. So Na plus cation, there are 3 of them. But sodium doesn't have any influence on acidity or basicity. So we're looking at PO4, polyatomic ion. We had 3 sodiums, so 3 ions with the +1 charge. PO4 will have a 3- charge to balance that out. Sodium has no acid-base properties. PO4 3- is not on the list of counter ions. It also doesn't have a hydrogen that it could give away as an acid, and it's negatively charged. So that all fits the category of a base. Yeah.
Can you just explain again why it is a 3-?
Yes, because in the ionic compound, there are 3 sodium atoms, and sodium is in the first column. It has a +1 charge. That means overall, the cation charge is +3, and this is a neutral compound, so the anion must have a -3. And this is one of the polyatomic ions. Yeah. Okay, so this is basic. So overall, the solution is basic. We have sodium without acid-base properties, and then phosphate with acid-base properties, which is basic. So overall, the solution would be basic. For the third one, potassium, which is on our list of counter ions with no acid-base properties. It is the cation of a strong base, potassium hydroxide. So no acid-base properties. And then ClO4- is the anion of a strong acid. So if we look back to the chart, ClO4- is one of these counter ions that's considered a spectator ion that doesn't have acid-base properties. So that salt, this ionic compound, is neither acidic or basic. It would be neutral. It would not influence the acidity of solution. Okay, any questions on this slide? Okay, so you may approach a problem like what's on the next slide, where it says this salt is added to solution, sodium acetate. Sodium with a +1 charge, and then acetate -1 charge. So this is a 1 molar solution of sodium acetate. We're determining the pH. So to determine pH, we need concentration of either H3O plus or OH minus to eventually get to pH. So if we have sodium acetate in solution, what does that look like to you? Does that look like a basic or acidic compound? Keeping in mind that sodium does not have acid-base properties. Any thoughts? All right, that's all right. So sodium, no acid-base properties, we can ignore sodium. What we need to focus on is the acetate part, so that anion. One thing to consider is that bases are typically negative or neutral. That is a negative ion, so that is likely a base. Also, they gave us the Ka for acetic acid, which I know I didn't write out, but acetic acid is, actually I'll write it across the top, HC2H3O2. And so if this is a weak acid, but if you add it to solution, it dissociates and will form H3O plus and C2H3O2 minus, the acetate ion. So if acetic acid, it says in the name that is an acid, then the conjugate, the negative, that anion in that first reaction that I wrote up there would be the conjugate base. And so sodium acetate, which contains that polyatomic anion, would have basic properties. Okay, so that's the conjugate base of acetic acid. So sodium acetate will be basic overall. Okay, now we need to think about what happens when sodium acetate is added to solution. Well, we know it's going to separate into ions, so we don't even need to include sodium in the reaction equation, but I will. It's a spectator ion. It balances charge, but it doesn't react with anything. So it'll separate first into the ions. So adding that to water, we've got a weak base. It will react with H2O as a base, meaning it will take a hydrogen from H2O. and become HC2H3O2 minus, or not minus, neutral. And then water will become OH minus. And then we have the spectator ion that we care very little about. So in order to write this properly, we needed to first identify that acetate would act as a base. So adding acetate, the ion to solution, will be a base when it reacts with water. So that means, definition of a base, a Bronsted base, is that it accepts a proton, so it will become HC2H3O2, which we call acetic acid. And then water loses a proton and becomes OH minus. So to name everything, Na plus is spectator, acetate is the base, water is the acid, it gives away a proton. Then we have the conjugate acid, conjugate base, and then spectator. And we're still setting up the problem. We need to calculate pH. We do know the concentration of sodium acetate, but this is a weak base. It will reach equilibrium. We need to determine equilibrium concentration, so we need an ice table. We need ice tables for weak acids or bases that reach equilibrium. Now, normally when I write out the ice table, I include everything in the reaction equation. I'm going to keep it simple. We're going to ignore the spectator ion. That doesn't do anything. And I'm going to remove water from the ice table because that also doesn't influence equilibrium. When I have included water, we just don't add anything to that column. So I'm just not going to add it this time. But we need everything else. So acetate ion, acetic acid, and hydroxide. So I just left out spectator and water as a liquid. All right, so we know it's a 1 molar solution of sodium acetate. So we have 1 molar acetate. And then we initially don't have an either of the products. To reach equilibrium, we have to use up reactant and produce product. So negative X for reactants, positive X for products. And then we're not provided any equilibrium concentrations. So this is one of those problems where we have to write out equilibrium concentrations including X. So 1.0 minus X for the reactant and then just X for each product. Then we'll have to use the ratio of these using K, solve for X, solve for equilibrium concentration, which we'll do in a moment. There's one more thing we need to do before we can solve for X. So we're provided Ka for acetic acid, which is the product. The conjugate acid is acetic acid. Acetic acid is not what we're adding to solution. And remember, Ka is the equilibrium value constant for an acid added to solution. But we did not add the acid, we added the conjugate base. So we can't use Ka, but we can use Ka to find Kb, and we need to use Kb. B for base, A for acid. So in a previous slide, we wrote out this relationship that for an acid, or for a molecule that can be an acid in a conjugate base, Ka times Kb equals Kw. And Kw is the provided value is on your equation sheet, 1.0 times 10 to the negative 14. So we need to solve for solve for Kb. One point zero times 10 to the negative 14 divided by Ka, 1.8 times 10 to the negative 5. Kb 5.6 times 10 to the negative 10. So this is the K value, the equilibrium constant for acetate, the base C2H3O2 minus added to water solution. So the ratio of products to reactants is this value for acetate. So now we can say that Kb equals concentration of products over reactants at equilibrium. And at equilibrium, concentration of the products are each x, and then reactant is 1 minus x. So that will be x squared over 1 minus x. And then, since we have a weak base, this is a case where x is going to be much smaller than the initial concentration. So we can approximate the denominator as being equal to 1, because 1 minus a really small number is approximately 1. So we're saying this is approximately x squared over 1. And this is equal to Kb, which we calculated 5.6 times 10 to the negative 10. And now we can solve for x. So multiplying both sides by 1, we have x squared equals the same value. So we take square root of both sides. X is 2.4 times 10 to the negative 5. And I need more room, so I have to add a slide here. Okay, so before I go to the next slide where all of this is gone, just remember we first identified that sodium acetate has basic properties. So when you add sodium acetate to water, it will act as the base, take a hydrogen from water, and produce OH minus ions. We need to set up the ice table to find equilibrium concentrations, and we needed to find Kb because base was added to solution. because we need Kb because what's added to solution is a base. And using Kb, we solve for x. So now that we have x, we have equilibrium concentration of all three components. Remember, our goal is to calculate pH. With the hydroxide concentration at equilibrium, which is just equal to x, we could directly find POH and then find pH. Or, knowing concentration of hydroxide at equilibrium, we can use Kw to find H3O plus concentration and then calculate pH from that concentration. When we've done this before, I showed you both methods. I'm just going to use the POH route this time. So knowing OH minus concentration, I'm going to write that on this next slide, which is equal to X, which is 2.4 times 10 to the negative 5 molar. Remembering that we need pH. With the OH minus concentration, we can calculate POH. Which I didn't do. 14 minus. We get 4.63 for POH. And then we use relationship pH plus POH equals 14. So pH equals 14 minus POH, 4.63. And we've got pH. Questions on this problem? Still, at its most basic part is an ice table. We're just complicating a little bit beforehand, right? We need to determine that we have a base. We're not told it's a base. And a little bit after, so we had to calculate Kb to find equilibrium concentrations, but just merging a lot of concepts together here. So I know most of you plan to take organic, and I keep bringing that up because I am hoping to prepare you for your next chemistry class. We do a lot of math in Gen Chem, and when you get to organic, there's very little math. So you probably won't have an ice table when you go to organic chemistry. My students don't do ice tables. But we will talk about how some acids are stronger than others and some bases are stronger than others based on the structure of those molecules. So it's more conceptual. This is what our next section is in this chapter. Instead of calculating the concentration at equilibrium or the pH of the solution, which you might do, but a lot more of what you'll be focused on in the acid-base unit is comparing two molecules, which acid is stronger, comparing two acids, or comparing two bases, which base is stronger. And there are a few different factors that we'll consider, which we'll get to in the next couple of slides. And then another thing to keep in mind is we have this umbrella. If we're just talking about acids, for example, we have a strong acid umbrella. We have a weak acid umbrella. But within all of the weak acids, some are stronger than others. within all of the strong acids, some are stronger than others. And then these properties that we're about to talk about will help determine why that's the case and explain chemically why some acids are stronger than others. So relating acid strength to structure. The first factor, so let's see, we have 4 factors that we'll talk about. The first factor is bond strength. And we're talking about the bond between the hydrogen that would get removed by a base and whatever that is bonded to. If that is a stronger bond, it's more difficult for a base to remove that hydrogen. So that means that acid with a stronger bond to hydrogen will be a weaker acid. It's less likely to give away a proton. Being more likely to give away a proton or give away a hydrogen makes something a stronger acid. So on the slide we have 3 strong acids and then HF, which is listed as a weak acid. HI bond energy, so higher bond energy means stronger bond. HI bond energy is lower than HBr, which means it's a weaker bond, and as a result, the acid is stronger. We have a lower pKa. And then same thing for, that carries out through the trend, but let's look at HCl and HF. HCl has a lower bond energy, that means weaker bond. That means easier to break the Cl to H bond. That means stronger acid. HF is a weaker acid. So to write all that down, let's write stronger bond to the acidic hydrogen. So the one that will be removed by a base. This means that more energy would be required to remove that hydrogen. So that will be a weaker acid. More energy is required to remove it. It's harder, more difficult for a base to remove that hydrogen. So that means it's a weaker acid. It's not as good or not as likely at giving away or to give away the hydrogen. And then the opposite would be true, weaker bond, less energy required, that would be a stronger acid. Okay, another trend is the anion size, and we're going to think about this in 2 ways. I'm going to turn my phone on silent. My family chat is going crazy. Okay, so anion size. There are 2 ways that we'll think about this. This is related to the atomic size. We have iodine, which is low on the periodic table. That's a big molecule, or that's a big atom, bonded to hydrogen. That's a much longer bond than if hydrogen is bonded to fluorine. So it's a longer bond. That's a weaker bond. Just goes back to what we discussed on the previous slide. Longer bond, weaker bond, easier to remove hydrogen. Okay, I've got a lot of things on the slide here. So larger atom bonded to acidic hydrogen, like iodine compared to fluorine. Iodine is a larger atom. That means the bond to the hydrogen is longer, which means the bond is weaker, which means it's easier to remove the hydrogen, which means stronger acid. Another property of these ion sizes, or another implication of having different ion sizes, is the stability of that ion. So in all of these cases, hydrogen, or HI, let's say, for example, as a strong acid becomes H plus and I minus. HF becomes H plus and F minus. So all of these anions have an extra electron in their outermost shell. That electron being in a larger shell. So think about fluorine, real nice and small. Outermost electron is really close to the nucleus. It's in the second period. Iodine, real large. Outermost electron is much further away. This is the nucleus. This is the outermost electron. Having that extra electron in a large orbital is stabilizing. So iodine as an anion is more stable. This electron, high energy electron, has more space to move around, is more stable than fluorine with a negative charge because that electron just has a little bit of space. So if we're taking an acid like HI, separating it into H plus and I minus is more stable than F minus, then we're producing more stable products, and that makes HI more likely to dissociate into those ions, producing more stable. Reactions are looking to become more stable, so if we can have a more stable anion as a product, that will result in having a stronger acid. So larger anions are more stable with a negative charge. So it is easier to remove hydrogen from the acid to form the anion, which means stronger acid. Sorry, that's really small. So the trends work both ways. Iodine's a larger atom, so it has a weaker bond to hydrogen that's easier to break. And iodide with a negative charge is more stable, which is another reason why HI is a stronger acid. This is most relevant when comparing atoms in the same group. So all of the atoms that we're comparing bonded to hydrogen are halogens. They're all in the same group in the periodic table. So you go down the group, atomic size is an important influence on the property of those atoms. The next trend that we'll talk about is relevant for comparing atoms in the same row. So down a column, you want to compare anion size. Across a row, we're thinking about electronegativity. So we'll talk about that in a moment. Okay, so now the bond that holds the hydrogen atom, the polarity of that bond influences acidity. So in this molecule here, this is acetic acid, which we were just talking about. There are 4 hydrogens. 3 of them are bonded to carbon. 1 of them is bonded to oxygen. All 4 of these hydrogens don't have the same acidity. The one that has a more, or is part of a more polar bond, would be the more acidic hydrogen. So that's this one here. Hydrogen to carbon bond is not very polar, but hydrogen to oxygen bond is very polar because of oxygen's electronegativity. So adding in the dipole arrow, the electronegativity, the electrons are closer to oxygen. That induces a partial positive charge on hydrogen and partial negative on oxygen. Stronger partial positive charge means two things. One, it's easier now, requires less energy for this hydrogen to become fully positive, aka H+, be removed by a base. And two, bases have electrons that create a bond to a hydrogen. This having a partial positive charge is now more attracted to the base with a negative charge or having electrons which are negatively charged. So, to read what's on the slide, the bond that holds the H atom, if that is highly polar, the H will have some partially positive character, partially positive charge, making it easier to fully ionize to H+. And then the more polar the bond between hydrogen and its bonding partner, so the other atom it's bonded to, the more easily ionizable the hydrogen will be, which means more acidic. So the hydrogens bonded to carbon with pretty much a nonpolar bond are not acidic. These have really low acidity. This has high acidity. So stronger acid, weaker acid. So if you're looking at this molecule, this is the acidic hydrogen that would be removed by a base. Okay, one more factor. This is called inductive effect. Okay, so looking at the chart here. The first molecule up there is acetic acid, same molecule that we looked at on the previous slide, and we identified the hydrogen bonded to oxygen is the acidic hydrogen. And that's the case for all of the molecules on this slide. Well, let's look at the difference between each of these. So first we have acetic acid. Next we have chloroacetic acid. One of the hydrogens that was bonded to the carbon is now a chlorine. We look at the Ka values. Remember, Ka is equilibrium constant for an acid. Higher Ka means stronger acid because you have more products at equilibrium. The Ka, I'm just going to compare exponents. Without chlorine is 10 to the negative 5. With chlorine is 10 to the negative 3. So adding one chlorine atom increases the acidity, increases the Ka by an exponent of 2. There are 2 chlorines added to that carbon. Exponent is negative 2 compared to negative 3. And then 3 chlorines, exponent is negative 1. So these chlorines, they're added to the molecule, but they're not directly bonded to this hydrogen. This is what we call the inductive effect. These chlorines, electronegative atoms, so this happens when electronegative atoms are bonded in the molecule, not directly to the hydrogen. They pull electron density, I'm going to say it over here, they pull electron density away from the hydrogen, the acidic hydrogen, making its partial positive even stronger. So through the molecule, because they're electronegative, they pull electron density, and that's what the inductive effect is. Pulling electron density through the molecule, making this more positive. Okay, so if surrounding atoms are highly electronegative, they draw electron density away from the acidic hydrogen, which gives that hydrogen a stronger partial positive charge, and thus is easier to fully ionize to a proton. So if you have a greater number of electronegative atoms surrounding the acidic hydrogen, this would mean that acid is stronger. So this can increase the acidity of the overall molecule by adding those atoms in. All right. Now notice the names here, not that you need to remember them, but this is fluoroacetic acid, this is dichloroacetic acid, 2 chlorines. This is trichloro, because we have 3 chlorines. Okay, so summary on the next slide of all these trends: weaker bond, stronger acid, larger anion, stronger acid, electronegativity, more electronegative, stronger acid, and then more electronegative atoms elsewhere, also stronger acid. All right, so let's do this learning check. One of them is the iClicker, this one here. So you're comparing other acetic acid analogs. So there are 3 questions. Let's do this one first, just because we're at the end, towards the end of class. What factor are you considering when you compare these acidities? The names might help you because they look kind of similar to the previous slide, and I have acetic acid up there. So, and you have the formulas. So consider that. And then which one do you think is strongest? Which one do you think is weakest? While you're working on it, I will pass back assessments. Don't forget to answer this question though. And then in 3 minutes, I just have a slide to go over a couple of things from the assessment. As I pass them out, just to be respectful to everyone in the class, try to keep your reactions to yourself and react outside of that. But he will be available probably after 2 step other class. So then let me know if there's any questions. Okay, let me go over a couple of things for the exam real quick, and I'll leave the iClicker open. Don't forget to finish it for credit. Whoops. Where is it? Oh, maybe I don't have it in here. All right, give me a second. Okay, so it was out of 60 points. There are 18 multiple choice questions. Each question was multiple choice question was worth 2.666667 points. So, and then the 2 short answer questions are worth 6 points each. I'll explain this when we come back just because we don't have time. But one of the questions I accepted 2 answers. So it was on form 1 it's question 3, on form 2 it's question 4. The correct answer was that NO3 and oxygen are intermediates, but oxygen is also a product. And so one of the things that I said in our class made that answer hard, like difficult to select. So I accepted this one as well because oxygen is both an intermediate and a product. But I'll explain that in more detail when we come back. All your scores are already adjusted. So those will be posted on Blackboard also after 2 p.m. And then definitely look at the key. Let me know if you have questions.
Yeah.
보이잖아 여기 앞에. 야, 너 평소랑 좀 다르다.
No, Sarah's been under it. We can't. Do you submit?
Wait, let me do it. Okay.
Okay, thanks.
감사합니다.